Okay, we're going to carry on with Chapter 9, Section 9.5, MOSFET analog switching. If we look in our textbooks on page 459, introductory paragraph, MOSFETs are widely used in analog and digital switching applications. In the preceding section, you saw how MOSFETs are used in the switching mode in a Class D amplifier. Generally, they exhibit very low on resistance, very high off resistance, and fast switching times. Exactly what we want from a switch, no? So those characteristics, very important. Anyway, let's have a look at the MOSFET switching operation. E-MOSFETs are generally used for switching applications. Please take note of that. E-MOSFETs, not D-MOSFETs, because of their threshold characteristics, if you can recall from the previous chapter when we discussed the characteristics of the MOSFETs. VGS threshold. When the gate to source voltage is less than the threshold value, the MOSFET is off. And when the gate to source voltage is greater than the threshold value, the MOSFET is on. All right, and we can see it here on the on figure 932, switching operation on the load line. So here I can see in the ohmic region, RDS is very low and the MOSFET is like a closed switch. So I will use it in this area. So on, switch is on, or the switch is off. I'm not going to use it in between here, no? So I'm going to use it as a switch. So at or below VGS threshold, RDS is very high resistance, act like an open switch, and those are the two conditions that we are going to use the E-MOSFET. All right, so take note of figure 932 as well. All right, when we turn the page to page 460, just the characteristics there again of an ideal switch. Ideal switch, when the gate voltage of the N-channel MOSFET is a positive voltage, the gate is more positive than the source by an amount exceeding VGS threshold. That is important, né? Exceeding VGS threshold. If you remember the characteristic curve in the previous chapter. Alright, there the MOSFET is on and appears as a closed switch between the drain and the source. When the gate voltage is 0, the gate to source voltage is 0 volts, the MOSFET is off and appears as an open switch between the drain and source. Alright, that is for an N-channel, of course. As we can see here in figure 933, N-channel and the switch equivalent. You can see positive voltage on acts like a closed switch, 0 voltage on the gate acts like an open switch, N channel. Of course, the P channel is the other way around, 0 closed switch, positive voltage on the gate acts like an open switch. Please take note of that on page 460. Alright, that was the ideal switch. The analog switch, also just below figure 933, MOSFETs are commonly used for switching analog signals. Right? Basically, a signal is applied to the drain and can be switched through to the source by a voltage on the gate. Major restriction is that the signal level at the source must not cause the gate to source voltage to drop below VGS threshold. Please underline that. That is important. The major restriction is that the signal level at the source must not cause the gate to source voltage to drop below VGS threshold. Alright, in figure 938 is a basic N-channel MOSFET shown, analog switch shown. The signal at the drain connect to the source when the MOSFET is turned on by a positive VGS and disconnected when VGS is 0 as indicated. You can see there. When it is 0, you can see my input signal is not passed through, but of course when I have a positive voltage, and as long as this voltage is higher than the threshold voltage VGS, my signal gets passed through this device. Acts like an analog switch. But important, that last paragraph at the bottom of the page, please underline that. In connection with figure 935, what I've just shown you, but we will have a look at it again. When the analog switch is on, as illustrated in figure 935, the minimum gate to source voltage occurs at the negative peak of the signal. The difference in VG and minus V peak out is the gate to source voltage at the instant of the negative peak and must be equal to or greater than VGS threshold to keep the MOSFET in conduction. So please take note of that. The figure is on the next page there. This is what they're referring to now. Voltage at the gate must be equal or larger than the minimum V peak out of my signal that I want to pass through this analog switch. So please take note of that, very important. Alright, on the next page, 461, analog switch applications, some applications where analog switching is used. Right, one application of analog switches is in analog to digital conversion. The analog switch is used in a sample and hold circuit to sample the input signal at a certain rate. Each sampled signal value is then temporarily stored on a capacitor until it can be converted to digital code by an analog to digital converter. Now, some of you, I'm sure, are taking the digital courses at the computer school. You should be more familiar with this. But actually it's not that difficult, as we've seen what the operation is. So I have gate pulses here. You can see here, there's the pulses on the gate. And there's my input signal, also displayed on that side. So for these pulses then I can see that I get a sampled output signal. There's the switch is on for that specific part of the circuit, and I get a sampled output signal. Of course, when the gate pulse returns to 0, I can see also my sampled output signal also returns to 0. Until I get the next pulse, take the next sample, and I have the next sample output signal. And so I get samples of my signal passed through to the output of my analog switch. Important though, mark the last paragraph there at page 461 as well. The minimum rate at which a signal can be sampled and reconstructed. That's important, eh? Sampled and reconstructed from the samples must be more than twice the maximum frequency contained in the signal. Right, so the minimum sampling frequency is called the Nyquist frequency, and you can see the F sample minimum should be at least 2 times the frequency of my input signal. So, when a gate pulse is at a high level, as we've seen, you can just perhaps mark that, as we've seen in the figure that I've shown. The switch is turned on and a small portion of the input waveform occurring during that pulse appears on the output. When the pulse waveform is at the 0 level, the switch is turned off and the output is also at 0. That's just what I've shown you what I've shown you here. No? So I get a sample at that pulse, sample is taken at the output, but of course when the gate pulse returns to 0, I can see that I also have it 0 on the output signal waveform. That's all that they are telling us there. Alright, then still on page 462, analog multiplexer. We're not going into depth into these devices. It's just introductory, so you get some basic knowledge. These things can get quite involved, but you will get to work with them in some other subjects after electronics too. But we have to do the introduction so that you at least know the basic theory. Anyway, analog multiplexers are used where two or more signals are to be routed to the same destination. Now this, for example, can be used in a telecom line where, say, 2 or 3 or 4 people are using the same telephone line, the 4-wire telephone line, so that they all get onto the same line. Multiplexing, we will see how it works now. One example. So for example, a 2-channel analog sampling multiplexer is shown in figure 937. The MOSFETs are alternatively turned on and off so that the first signal sample is connected to the output and then the other. The pulses are applied to the gate of switch A and the inverted pulses are applied to the gate of switch B. A digital circuit known as an inverter is used for this. When the pulses are high, switch A is on and switch B is off because of the inverter. And when the pulses are low, switch B is on and switch A is off. So if we go and look at that circuit, I can see here different colors, although not that clear on the board. There's my A, there's my B applied, but see what happens here is this pulse signal that's applied here at the gates without an inverter to MOSFET A, but via an inverter to B. So what the inverter inverts that pulse signal. So what happens is then for one pulse, A is switched on, and I get a portion of the signal on the output. So I can see there. And for the red one, maybe it will be more color. The colors are more clear in your textbooks. I will get with the inverted circle, then A will be off and B will be on, and I get my next sample. But you can see that the one after the other, they're not on top of each other, they're multiplexed. So this is called time division multiplexing. Time division multiplexing, you can underline that paragraph as well, just above figure 937. Because signal A appears on the output during the time intervals when the pulse is high, and signal B appears during the time signals when the pulse is low. That is, they are interleaved on a time basis for a transmission on a single line. Right, that's multiplexing. All right, another one, switched capacitor circuit. The bottom of the page, page 462. Another application of MOSFETs is in switch capacitor circuits commonly used in integrated circuit programmable analog devices known as analog signal processors. Because capacitors can be implemented in ICs more easily than a resistor, they are used to emulate resistors. Capacitors also take up less space. You must please underline this, it's important. Capacitors also take up less space on a chip than an IC resistor and dissipate no power. Many types of analog circuits use resistors to determine voltage gain and other characteristics, and by using switched capacitors to emulate resistors, dynamic programming of analog circuits can be achieved. Now you've done capacitor and capacitor characteristics in electrical engineering 1, and those were one of the factors that you were supposed to learn there as well. So if you can't remember, you'll have to go and do some revision. All right. For example, in a certain type of IC amplifier, these IC amplifiers will be discussed in Electronics 3 again. So, but this is just an application just to show you where these switch capacitor circuits are used. 2 external resistors are required as shown in figure 938. The values of these resistors establish the voltage gain of the amplifier. As I said, this theory is taught in Electronics 3, so don't worry about that. It's just to show you the application at this stage. Alright, so that is the application. There's a type of IC amplifier. Perhaps we can show it here. there's a type of IC amplifier. And my concern is here, because it's an integrated circuit, are these resistors. As we've seen, they take up a lot of space and they generate heat. So I would rather use the switched capacitors. Alright, if we refer back to the textbook, a switched capacitor can be used to emulate resistors as shown in figure 9. 39, using a mechanical switch analogy. MOSFETs are actually used as switches, as we will see a bit later. Switch 1 and switch 2 are alternatively turned on and off at a certain frequency to charge or discharge the capacitor, depending on the values of the voltage sources. In the case of R1 in figure 938, V in and V1 are represented by VA and VB respectively, and for R2, V1 and V out are represented by VA and VB respectively. Alright, so as we've heard, these switches actually, we're going to use MOSFETs to charge and discharge this capacitor, in other words, to change the value of the resistor as I need for that specific circuit, amplifier circuit. Alright, if we refer back to the textbook, you should be familiar with this. It can be shown in Appendix B in the back of the book that the capacitor emulates a resistance with a value that depends on the frequency at which the switches are turned on and off, and the capacitance value. So there's the equation. R is equal to 1 over Fc. So you can see as I change the frequency, the value of R is also going to change. Alright, so how is this done? Complementary E MOSFETs and capacitors can be used to replace the resistors in the amplifier as shown in figure 940. When Q1 is on, Q2 is off, and vice versa. The frequency of F1 and C1 are selected to provide the required value of R1. Likewise, F2 and C2 provide the required value of R2. To reprogram the amplifier for a different gain, the frequencies are changed. Alright, so there is the application. As we can see now, the resistors now replaced by MOSFETs and capacitors. And I can then control, as we've seen according to the formula, the resistance by changing the frequency in both of these cases. Okay, so we've seen what the advantages are. Less heat generated, smaller, and so forth. Specifically for use on integrated circuits in these specific amplifiers. Alright, so that is another application of the MOSFETs in analog switching. So as we can see, basically just again theory in that specific section. So please read through the sections again, work through there, although there are not that many examples, and then of course do the relevant basic problems, in this case only from 34 to 37. Alright, that concludes then MOSFET analog switching.